All right, CUET aspirants, listen up. The exam's getting closer. I know the pressure's building, and there's one tricky little section of the periodic table that just loves to gobble up marks. I'm talking about the F block. Lanthanoids, actinoids. On paper, they kind of blur together, right? Well, they're not the same. Not even close. And today, we're going to crack this thing wide open.
So you want to know the biggest trap here? The number one mistake that separates the top rankers from everyone else on these questions? I'll tell you right now. It has nothing to do with memorizing every single element. It comes down to a simple, fundamental misunderstanding of one single core idea.
And here's my promise to you. Stick with me for the next few minutes, and you won't just know the differences between these two series, you'll understand the one single reason behind all of it, the key that unlocks the entire F block. So let's get into it.
So let's call it what it is, the F block trap. Why? Because these elements look like they should be similar, but their chemistry, well, it tells two completely different stories.
Okay, the basics, super fast. F-block elements are just elements where that last electron you add goes into an F orbital. That's it. We've got two main families here, the lanthanoids, which fill up the 4F orbitals, and the actinoids, which fill up the 5F. Think of them like two different branches of a family tree with very, very different personalities.
First up, let's meet the lanthanoids. I like to call them the stable family. They're pretty predictable. You know, they mostly like to follow the rules. And here's the secret to their whole vibe. Those 4F orbitals are buried deep inside the atom. Imagine them kind of locked away in a vault, with the 5s and 5p orbitals standing guard outside. This means those 4F electrons are shielded, they can't really get out and play, they don't participate much in bonding. And that's what makes them all so chemically similar. It's the very reason they're so tough to separate from each other in the real world.
So, if you remember one thing, tattoo this on your brain. The lanthanoids' favorite number is +3. It's their go-to, their most stable, their default oxidation state. But here's the thing about exams like CUET, they don't care about the rule. They want to know if you know the exceptions.
And here are the two rebels you absolutely have to know. You've got cerium, which can hit a +4 state. Why? Because by losing that fourth electron, it gets a super stable, empty 4F subshell. Chemistry loves that. Then you have europium, which can do a +2. This leaves it with a perfectly half-filled 4F7 configuration, another thing chemistry finds incredibly stable. Okay, pause and think moment. Why is a half-filled or totally empty subshell so stable? Think about symmetry. Think about balance. That's what it's all about.
All right, let's reset for a second. We've talked electrons, now let's shift gears to their physical size. Because there's something really weird that happens as you go across the lanthanoid series, a kind of shrinking atom secret. It's called lanthanoid contraction. And I can almost guarantee you'll see this on your exam. It's a huge concept. As you move across the series from left to right, the atoms and ions actually get smaller. It's this steady, gradual, predictable shrink.
But wait a minute, that doesn't really make sense, does it? We're adding protons, we're adding electrons. Shouldn't the atoms be getting bigger? What on earth is causing them to shrink?
And the culprit is something called pore shielding. Those 4F electrons, because of their weird spread-out shape, are absolutely terrible at their job. Their job is to shield the outer electrons from the pole of the nucleus, but they fail miserably. So as the positive charge in the nucleus gets stronger with each element, it just pulls everything in tighter and tighter. The whole atom gets squeezed. That's the secret.
Okay, so we've met the stable family. Now let's meet their cousins, the wild bunch, the actinoids. And if the lanthanoids were predictable, these guys are, well, they're chaotic, unpredictable, and a little bit dangerous.
First thing you need to know, and it's a big one, all of them are radioactive. Every single one. No exceptions. So if you see radioactive in a question, your brain needs to immediately scream actinoids. But the real source of their chemical chaos is that their 5F, 6D, and 7S orbitals are all super close in energy. It's like a traffic jam of electrons ready to go.
And because those orbitals are all mashed together in terms of energy, electrons from all of them can get involved in bonding. So you can forget about that nice stable +3 state. The actinoids threw that rulebook out the window. They show a massive range of oxidation states, going all the way up to +7 sometimes. All right, another pause and think moment. Why would having more electrons available for bonding make their chemistry so much more complicated? Okay, pop quiz time, super quick. Based on what we just said, which series shows a bigger variety in its oxidation states? Is it A, the lanthanoids, or B, the actinoids? Lock in your answer now.
It's actinoids. Of course it's the actinoids.
It all goes back to those 5f, 6d, and 7s orbitals being so close in energy. They just have more tools in their chemical toolbox, which leads to way more possibilities.
Okay, time for our final attention reset. Let's bring it all home. Let's put these two families side by side for the final showdown. This is your ultimate revision tool.
You should probably screenshot this slide. This is your cheat sheet. Let's run through it. Orbitals, 4f for lanthanoids, 5f for actinoids. Easy. Oxidation state, lanthanoids are mostly +3. Actinoids are all over the place. Radioactivity, a hard no for most lanthanoids, a hard yes for all actinoids. Contraction, they both do it, but it's even more extreme in the actinoids. And why? Because 5f electrons are even worse at shielding than 4f electrons. And all this means that, in general, lanthanoids are less reactive, while actinoids are more reactive. See? It all connects.
So what's the game plan to win on exam day? It is not about memorizing this entire table. No, it's about understanding the single reason behind the table.
Okay, remember at the very beginning, I promised you there was one core reason that explains everything. Well, here it is. The master key is the poor shielding effect of f orbitals. That one concept explains why they shrink, the contraction. And the degree of that poor shielding, the fact that 5f is even worse than 4f, explains why actinoids have more contraction, more variable states, and more complex chemistry. That's it. That's the whole story.
So if you walk away with just 3 things, make it these. 1. Lanthanoids are the stable +3 crew with that famous contraction. 2. Actinoids are the radioactive wild bunch with variable states. And 3. The ultimate why behind it all is poor shielding. Now keep that in mind for one final challenge.
I'm going to leave you with a real rank booster question here, a classic. Using what you now know about lanthanoid contraction, can you explain why the elements in the 5D series have atoms that are almost the exact same size as the 4D elements right above them? The answer is hiding in everything we just talked about. Think it through.
Look, you have the core concept now. You understand the why. That's honestly the hardest part. The key now is just to apply it. Go do your practice questions and you'll start to see these patterns everywhere. You've got this. Keep up the great work.